Hello and welcome to our webinar on InSAR for Architecture, Engineering, and Construction, also known as AEC. Thank you so much for being here from wherever you are around the world. Before we get started, just a quick note about how best to engage with our team. So your lines will be muted during the presentation. However, if you do have a question at any point throughout the webinar, please go to the GoToWebinar window, expand the questions section, and you can type your question directly into that panel. Ground displacement is both a threat to infrastructure and buildings as well as a common precursor of a potential event that might cause damage and failures. So it's important that we're able to both monitor for the actual threat itself, but also look for these very minute activities or very minute ground displacement actions that could indicate that there might be potential damage or a potential future failure that can happen. The amount of ground movement that can ultimately result in a damage or failure to infrastructure and buildings can be measured often on the order of millimeters or centimeters. Now, this is a not localized phenomenon. This is a issue that is global in its potential impact. As you can see by this map here, there's a variety of locations all throughout the world, particularly in North America, Europe, throughout Asia and parts of South America, where subsidence is, there's a very high risk of potential subsidence activities that need to be monitored. Now, the importance of monitoring ground displacement, so this is seen across a variety of different infrastructure and building assets and projects. So if we look at roadways, for example, so as you can see, subsidence can cause potholes, can cause significant damage, cracks, and basically accelerate the need for repairs. Now, just looking at the United States alone, over 40% of the US road systems are in poor, mediocre conditions. This is a $435 billion backlog. As we know, in the United States right now, there is a bill that's being passed to put a lot of money towards trillions of dollars towards infrastructure. What we can do, what subsidence can ultimately do with roadways is it can accelerate the damage. So by identifying where you have high levels of subsidence within particular roadways can ultimately help you identify where there might be or how to prioritize or where you should potentially prioritize construction and repair activities. If we look at bridges, this is another area where both subsidence can be detrimental to the actual to the structure itself, but it can also be an important precursor of a potential failure or very expensive damage. If we look at the United States, a very alarming number, about 46,154 bridges, or about 7.5% of the bridges in the United States, are structurally or considered to be structurally deficient. This impacts about 178 million different users of these bridges every day. Now, this is also really important now, being able to monitor these bridges and being able to identify these very minute or very subtle displacement events that can have or be a precursor to a potentially catastrophic failure. So that's very important. We look at buildings and properties. So a lot of buildings and structures and of course infrastructure around it are built on top of underground areas that are impacted by subsidence or that cause subsidence. So a lot of these subsurface activities might include construction, so perhaps subways, mining activities, water extraction, oil extraction. So a variety of these different man-made activities can impact surface subsidence or cause unexpected surface subsidence. Of course, there's also a number of natural causes to surface subsidence that can impact these buildings that we're going to get to in a little bit. Now, just to give you an idea, in Western Europe, such as Germany, the UK, Poland, and a variety of other countries, there are over 5 million properties that are currently built on active or inactive mines that are potentially susceptible to subsidence activities. Now, climate change is ultimately making this problem even worse. This is not something that's just going to go away in the short term. This is something that is actually going to accelerate and become even more of a problem. So implementing solutions to help mitigate this as soon as possible is important so that we don't have high costs in the future. Just to give you an idea, many people in this webinar might be familiar with the impacts of permafrost, especially if you're from Canada. So looking at just in Alaska alone, they're highly susceptible and vulnerable to the potential impacts of permafrost, which ultimately is identified as subsidence. And if we look at the USGS, they're projecting that they're going to lose about 16 to 24% of the permafrost by the end of the century. Looking at the cost of repairing this, it's been projected that in Alaska alone, the cost could be as high as $5.5 billion by the end of this century to repair all of the infrastructure, such as roadways, that are impacted. Now, climate change is not just something that only the Arctic and subarctic need to worry about. More temperate climates also are impacted by climate change and realizing it or being realized as subsidence. Now, this is one example of that, where basically a concept known as shrink swell, which is basically the change in soil volume or the due to the amount of moisture in the soil. This is particularly impacts clay-rich soils, which are which basically, as they absorb a lot of moisture, they swell up and they actually expand. And as they dry out, they tend to crack and crumble, and that causes the subsidence. So this in the UK alone, just to give you another example of somewhere else in the world where this is a problem, is it's actually in the last decade been one of the costliest geohazards in the area. Costing about $4.15 billion in repairs and damages as a result. And if you look at this map here on the right, we can actually see that the projections for 2030 and 2070, respectively, that we're expected to see a major increase in the amount of areas that are likely or highly likely impacted by shrink swell subsidence, which is expected to hit about 10.9% of all properties within the UK. So this is just another example of the potential impacts of subsidence and that it's important in order to monitor this. What we are able to do is we can now leverage a very exciting technology known as InSAR using spaceborne radar in order to create cost-effective monitoring solutions where we can monitor vast amounts of infrastructure, buildings, construction projects, and capture new measurements on a regular schedule. And we can do this in order to detect abnormal ground displacement, or where ground displacement exceeds a certain tolerance and may become a risk factor for a particular type of failure, damage, or downtime. So if we look at a very obviously very generic example in this case, so looking at a standard, say, risk management and monitoring system, where you're looking at trying to identify, let's say for a bridge, trying to understand whether or not there's any impacts, or a dam might be another type of asset that would be monitored here, construction sites, etc. So you might so oftentimes these systems are taking in a variety of different inputs of different data types. So you might have geological makeups or geological maps of the area, seismic activities, what's the construction material that's being used, what's its shelf life, what's its age, weather and climate conditions, and then a variety of other sensors that would be leveraged, such as in situ sensors, and then also using ground survey crews. Now, what the value that we can provide here is we can now provide a new data source into these management and monitoring systems in order to basically monitor regularly ground displacement around a variety of different types of assets. Now, to look at a more specific example, now this is provided to us courtesy of Geotesta, which is a geotechnical engineering company. Looking at this one example here, this is a tunneling example. So this would be subsidence, man-made type of subsidence that can be occurred due to underground or subsurface activities. So right now, when there is a tunneling activity, whether it's for a subway or something, or a different type of infrastructure, there's a variety of sensors that are already being used, and we can just see just a subset of some of the sensors that are being used here, such as tilt sensors on buildings to measure if the ground subsides due to the tunneling activities, as the sediment settles, to see if there's any tilting on the buildings, measuring the settlement itself. So what's the amount of settlement that's or what's the measure of the settlement on the surface, and then a variety of other sensors and measurements on the ground to just understand what the impacts are of these activities. Now, some of the challenges about this today is with this conventional monitoring is that a lot of times with when these construction projects are initiated, there is no history. There's no historical data to leverage. These sensors are being put in place for the first time, so they don't have any idea as to what the long-term or what kind of subsidence is characteristic of this area. Same thing, these sensors are very expensive to install, and they're put in very discrete or limited locations. So as a result, you only are getting, you might be getting real-time feedback of where the sensors are actually located, but they need to be installed in very strategic locations. And then as a result, you end up having a lot of no data areas where you basically don't have any information about, more localized subsidence that might be occurring in those areas. And then same thing, if you're trying to track a very large or monitor a very large area, it can become incredibly expensive to do this using in situ sensors and ground crews. This is where InSAR can really help, is that InSAR can help fill in these data gaps, and in some cases might even be able to help minimize the reliance on some of these sensors and ground surveys. So some of the benefits is we can also untap decades of historical measurements themselves. So being able to look back in time and understand what kind of subsidence has been happening in particular areas going back decades, so that can be taken into consideration in engineering, design, or modeling. We can also reduce the reliance on expensive sensors. So we're not, you still need certain sensors, but when we look at some of the surface sensors measuring displacement and settlements, you might not need as many. Perhaps you have some for helping to calibrate as well as helping to validate the measurements of your InSAR measurements. But certainly there's a cost reduction that can be expected. And then the other benefit is we can also monitor very, very large areas at a very cost-effective manner, which we're going to actually showcase in just a moment. So what we are able to offer is access to reliable millimeter level measurements. We can provide large coverage areas. We can monitor nearly anywhere on Earth. We can provide high density measurements that are updated regularly. And with the new constellations, SAR constellations constantly going up, new satellites going up, the ability to get new measurements is increasing significantly. So the window between measurements, or the frequency of measurements, is going to very quickly get to daily measurements, and potentially even same day measurements for certain in the not too distant future. And then of course we can go back in time and provide decades of historical data. Now there's this concept here that we want to just quickly talk about. It's one of the benefits of leveraging our technology, our systems, is that we have, because of the way that we've designed our technology, and because we've been supporting these sensors for over, essentially almost 4 decades, we have a sensor agnostic approach to our science. And essentially, this allows us to leverage and create concepts such as TipQ, which is the idea of using medium resolution, less expensive, either commercial or even freely available open source data to do more general trend mapping over very large areas, as you can see here by this map. And this provides a very cost-effective way to just, in general, monitor very, very large areas to see if there's any particular areas that are starting to see potential subsidence activities. Now, and then if you do identify that there's an acceleration in subsidence or an increase in the velocity of subsidence or ground displacement of any kind in a particular area, you can then procure through our services, procure commercial data, very high resolution commercial data, to then do a much closer inspection. So in this example, we're using 14-meter Sentinel-1 imagery, which is an open source format that's freely available, and calculating our ground displacement for a very large area, as you can see here. And then as we identify particular areas where there's an acceleration in ground subsidence, we can then zoom in on that area using very high resolution commercial data, such as this 3-meter terrace RX imagery, and it gets much higher. We can even get down to 25 centimeters if need be, and start to capture many more measurement points on top of particular features of interest, such as buildings, bridges, and other kinds of construction sites and infrastructure projects. So with that, I'm going to hand things over to Kevin, who is going to walk you through our demonstration.
For today's demonstration, we're going to be focusing on the greater Miami area. This is along the eastern seaboard of the United States, and it's a very susceptible area in terms of ground displacement and subsidence as identified in that study and the map that Sean showed previously. This is a medium to high risk area due to the fact that there is quite a bit of infrastructure, expensive infrastructure within this part of Florida, in addition to quite a lot of expensive real estate. The study area overlaps 2 UNAVCO GNSS stations. These are continuous monitoring stations that collect ground displacement data on a very, very frequent interval, roughly every 30 seconds. So we can use that data to calibrate our measurements from satellite imagery and also compare the measurements that we derive to the actual in situ measurements that are extracted from those stations. The imagery that we processed covers a time period from December 2020 to June 2021. This is a 16-image Sentinel-1 stack, which is the lower resolution satellite that we use. And in addition to that, we have a higher resolution data set collected by TerraSAR-X. This is a commercial sensor that's owned and operated by Airbus Defence and Space, and it gives us a higher resolution set of measurements. So this is our Catalyst Insight web application. I want to walk you through a couple of different things. This is the area of interest that we processed over the eastern seaboard around the Miami area, which we identified as being high risk. And what you can see on the interface instantly is that it's very easy to understand some of the information. So what you can see here is a cumulative displacement map. What this is showing is how much the ground displacement is occurring over the different geographic areas. So if I hover my cursor, this tells you in millimeters per year, what is the displacement that has occurred over these different locations over this time period. So you can see here on the last acquisition, which I can select from the drop-down menu from June 21st, this is the total cumulative displacement over this particular location. We have this really nice tool that allows you to query the individual pixels. So if I wanted to see the elevation or the displacement profile over time for that particular location, what I could do is I can use my cursor and I can point to a location on the map, and then I can get the profile of that displacement that's occurred over this particular location. So I can click on any part of the map and get this kind of information. You can see that the range is about -5 millimeters or a little bit less than that, up to +15 millimeters. So not a lot of movement that's occurred over these blue areas. And then conversely, if I query an area that has some yellows or some reds, I can query those pixels, and then I can get a similar elevation profile. And you can see that the graph tells you whether the displacement is occurring upwards or downwards over time. You can see the trend, whether it's moving up or down. So that's a really nice feature that we can expose. Now, in terms of TipQ, this is a great tool that we can make available. What we can do is we can calculate the displacement information using Sentinel-1 over a large area, which is what you see on the screen here. And we can also calculate over specific hot zones where displacement is occurring. So what I want to do is focus my attention over in a location here in Miami Springs. So I'm just going to zoom into that area. And if I want to make it easier to display, I can just change the opacity on this particular layer and I can see through it. So I'm going to move around here and try to find a location that is of interest, that has some particular infrastructure where we can look at what the displacement values are. So over here we have some buildings. There's a bit of a trend here from the lower resolution Sentinel-1 data that's telling me that the displacement that's occurring here is about 45 millimeters over the time period. So what I can do is I can zoom in and I can turn on the individual persistent scatterer information from the Sentinel-1 data. So I can turn that layer on here, and I can get those individual measurements, and you can see what those values are over this location. And these buildings have measurements from the Sentinel-1 for sure. But then what I can do is I can turn on the TerraSAR X data and get a much denser and higher quality measurement over the individual buildings. So I'll zoom in just a little bit more to be able to pull those up. And you can see that the density of the points is much closer together, and it's much more concentrated on those persistent scatterers that are buildings. Just because of the resolution of the data, we're able to pinpoint the exact displacement measurements on those individual features of interest, which are the buildings or the key pieces of the infrastructure. So that's a key thing. What I can also do is I can kind of compare the values. So if I hover my mouse over the Sentinel-1 derived information, which is lower resolution, but does provide me information, I'm getting a value of about -47 here over that particular location. And then if I hover over some of the points that are derived from the TerraSAR X data, you can see that I'm getting very similar measurements around -40 millimeters of displacement over time. So this interface is very easy to use. You can see that we can turn layers on and off and query the data and export the data if we want to. We've got tools for basically selecting a number of points and then exporting those out to tabular form, or we can consume the data via an API like we showed earlier. Now, another thing that we can do is identify the potential risk. Now, in this case, we identified the risk to buildings based on the deformation or the displacement that we observed. That could be customized based on the displacement that is of concern for a particular type of infrastructure that is in place over a location of interest. So we've got non-Earth observation data that's displayed here, building footprints that we basically collected from the county GIS. And what we can do is we can intersect the displacement data, assign it a risk level based on the displacement that we're observing, and then flag the features of interest based on their current risk level. And that risk level can change over time depending on the displacement data that's being collected on a regular basis. So just a few words about InSAR. InSAR is interferometric SAR. It's a technique that's been developed over a number of decades by a number of scientists around the world. And what it leverages is the ability to process both the amplitude portion of radar images as well as the phase information. So if we collect an image over the same location multiple times in the exact same geometry, we're able to get not only the amplitude portion of the signal, but also the phase portion or the timing of the radar pulses being sent to the ground and then the echoes returning to the sensor. When those echoes return back to the sensor, if something occurs on the ground that causes a change, for example, a displacement on the ground, there can be a delay or an acceleration of that phase return depending on which direction the displacement is occurring in. And that's what you're seeing on the screen is essentially two different images. It's a very simplified illustration, but two images that are collected over the same location. An event has occurred on the ground. In the case of the second image, the ground has moved farther away from the satellite, and we can measure that small, subtle displacement away from the sensor in what's called line of sight, very precisely to within millimeters or centimeters. The specific algorithm that we are using is called Short Baseline Persistent Scatter Interferometry, SBAS, and it's a state-of-the-art technique that can consistently achieve very high accuracy ground displacement measurements. This technique has been developed to produce consistent data where atmospheric effects can cause a decorrelation of the signal over time. Radar is very sensitive to moisture, it's very sensitive to changes on the ground. And so if we don't have perfect conditions, arid conditions, which is not the case in the majority of the world, then what we can do is we can apply this technique to ensure that we get consistent measurement where we can using SBAS PSI. There's two components to SBAS that I would like to quickly review. In order to optimize the measurements, we need to take into account the spatial baseline, or the distance between the satellites when they collect the different measurements over the same location, but also the temporal baseline, how far apart those collections are. We're looking to optimize the level of coherence that we can extract from the data. So SBAS is basically a technique that allows us to select the best pairs among our stack. We can collect multiple images. What we're looking to do is to select the best possible images in our stack to have highly coherent measurements and generate highly coherent targets to then extract the information from the phase portion of the radar signal. So another way to look at the PSI algorithm and the way that we identify stable points is to think about it in terms of an image stack. So we do use multiple images over the same area. And when we co-register those images and we drill through the individual pixels across the different dates, what we find are some areas are very stable, meaning they don't change in terms of their feature on the ground, the way that those features provide returns back to the radar, while some areas are affected quite a bit in terms of what type of features they are, like vessels or vegetation, or areas that are prone to getting affected by moisture. Those areas are going to change quite a bit. So we use PSI as a technique to identify stable points, and we measure the displacement where those stable points are located. Another key part of the InSAR algorithm that we deploy is the ability to calibrate with in situ measurements. And here what we see is in our study area, we have selected two separate GNSS stations from the UNAVCO network, one in the northern part of our area of interest and one in the southern part. And what you can see are the GPS surveying points, that's the blue line, and then the individual InSAR displacement measurements that we have produced using satellite imagery, which obviously has a different temporal frequency. It's not collecting every 30 seconds, it's collecting every 12 days. And what we can do is we can use those GNSS measurements to calibrate our measurements from the satellite. We can also conduct independent assessments, produce the data using our techniques, and then compare them to the GNSS to make sure that they agree in terms of the range of measurements that are being provided, and obviously the measurements themselves, whether the trends are similar. And you can see on these various illustrations that the trends that we have calculated over this particular time series from December 2020 through to June 2021 do agree quite strongly. And all of these statistics are displayed there on the screen, so you can see the mean difference between the GNSS and the InSAR-derived displacement measurements. So one of the key things with our InSAR algorithm is to make sure that we are producing consistent results. So we do carry out independent validation using the synthetic aperture radar InSAR measurements to produce displacement data, and then we compare that independently to ground displacement data derived from GNSS or GPS stations. And here's a study that we recently published where we compared the displacement measurements derived from a TerraSAR X data stack from 2019 November to 2020 July. And we were able to compare that to the GNSS stations or the GPS measurements from a specific UNAVCO station. And you can see that the trends agree and the range of the values that we measured agree quite strongly as well. We have developed technology over a number of years to be able to support all of the various synthetic aperture radar sensors that are being flown and that are collecting data. You see some of the ones that are commonly used today for InSAR. Sentinel-1 is one of the most exciting satellites because it basically collects data on a very systematic basis specifically for InSAR, and that's the one that we leverage. It can produce data around the world. There's other satellites that can produce higher resolution data like TerraSAR X, which we're featuring, and others that are listed here as well. New satellite constellations such as Capella Space and ISI are very exciting because what what they can achieve with the constellation of satellites is a much higher temporal frequency or revisit over the same location with InSAR suitable data. So that means that we can go from 11 days or 24 days down to daily or every couple of days revisit, perhaps even shorter than that, depending on how those operators choose to orbit their satellites around the Earth.
So at this point, we're just going to wrap things up and just wanted to quickly highlight what we're able to deliver. So once again, through our Catalyst Insights product, our solution, you were able to provide reliable millimeter level ground movement measurements. We can provide, there's a variety of ways for you to consume this information. So we have, as Kevin displayed here earlier today, we have the Catalyst Insights web application where you can visualize, analyze, and interpret the measurement of the data feeds, so the ground displacement measurements. And we also have our API, which is made available through Amazon Web Services data exchange. And you can access and plug this API directly into your systems. So if you'd like to learn more, please do get in touch with us. You can either go to catalyst.earth/AWS to learn more about our solution. And then if you want to reach out to either of us directly, feel free to reach out to Kevin Jones at jones@catalyst.earth, as well as myself, Mohammed at catalyst.earth.
Okay, I got to go, Shab. It's question time in the.
Hello, everyone. Thank you very much. And now we're opening up the lines for some questions. So if you have any questions throughout we already had a number of questions that came in, so really appreciate that. And we're happy to now ultimately address these questions here. So I'm just going to take a moment to read through some of the questions that have already come in. So we have actually one that came in, which is not necessarily about InSAR, but I think this is a good one for Kevin. So as Capella, now it generates radiogrammetry pairs. Is Catalyst planning on supporting this technique for generating digital elevation models?
Sorry, Sean, I just need to hear that back one more time. Can you just repeat that one again, please?
Absolutely. So the question that came in is, as Capella is now offering radiogrammetry pairs, is Catalyst planning, or do we already support this technique for generating digital elevation models?
Yeah, good question. So we're aware that Capella is providing stereo pairs. We have not worked with any of the data yet. Our technology does support the ability to co-register same side collects and to be able to run our epipolar DM extraction off the data. So it should work. We have not tested it ourselves, and we haven't officially released that as part of our software as of yet. We do support Capella data, and we have plans to support that function, but we would like to make sure that the data runs through our system successfully before we officially release that. We do release the software on a regular basis, so we have a update available roughly every 2 months. So that functionality is, when it becomes available, will become available very soon.
Wonderful. So one of the other questions that came in is about the calibration. So you discussed calibrating the data with GPS stations, and if they are available, or if you have in situ measurements on the ground. Is there any other calibrations that are performed, such as calibrating with terrain and atmospheric conditions?
Yeah, so in terms of removing the effects of topography and orbital effects and atmosphere, we definitely have capability in our software processing pipeline to account for those effects. So we use external DEMs to essentially remove the topographic residual phase that has contributed to the measurements based on the topography contributing to the residual phase differences. So we use DMs to remove that, and we also perform orbital adjustment using our production pipeline to reduce the effects of any residual orbital effects. In terms of the atmospheric effects, in the webinar, I did talk about the technique that we use, which is PSI, which seeks to only identify suitable points where the interference with the SAR signal is not as prevalent given that those targets are persistently scattering in the same way. So we do take very much care to ensure that the measurements are consistent and take into account the calibration.
Wonderful. One of the other questions that came in was whether or not we worked with GeoFin3 data and how does it compare with TerraSAR3. So we do support GeoFin3. I hope I'm pronouncing that correctly. But we haven't necessarily tested it right now with this InSAR workflow specifically. We've done a number of tests with TerraSAR-X, and as Kevin demonstrated some examples here, when we work with calibrated data or we're calibrating it with GPS stations, we've been able to achieve a approximately just over or just under 2 millimeter level mean delta. And then with the uncalibrated, where it's not calibrated with GPS, we're able to achieve just over a 3 millimeter delta or mean delta compared to the GPS measurements. So thank you for that question. Another one, I think this would be great for Kevin. So you showed in this example that we did calibrate the data with 2 GPS stations in the area. Is that required in order to achieve accurate results, or can you also work with, so I guess maybe just a comment on what's the importance of using it, and can you get around if you don't have that in situ measurements?
Yeah, so I mean, ideally, a well-distributed set of calibration points that are in situ sensors will give you the best result. Absolutely, no question. That I think is a given. That's not the reality. The ability to get continuous monitoring stations all over the world that are well distributed, that always cover your AOI, is obviously a challenge. So we've implemented technology to do calibration of the InSAR measurements to account for any displacement that isn't reflective of what's occurring on the ground. We do have automated calibration methods in our software. Typically what we do is we select stable targets that are not changing relative to the rest of the scene. We use a specific technique for identifying those targets, and then we select those targets across the area of interest to calibrate the measurements if there aren't any GPS measurements available to help us with the calibration. And that's actually something that was done in that study that was referenced over San Jose. We calibrated the data using our own techniques, and then we independently verified the measurements that we derived from the InSAR displacement map to the GNSS stations and found very strong agreement.
Wonderful, really appreciate that insight. Another question that came in, this might be just a more of a clarification question. So this was around the displacement that we're showcasing. So they're wondering, is this horizontal displacement, vertical displacement? So what exactly does it mean when you're talking about displacement in this context?
Yeah, so what we do is we convert the line of sight displacement to a vertical displacement measurement. The horizontal displacement would require processing of both ascending and descending passes and the integration of the displacement values from both. So that's not what we showcased here today. We primarily showcase the line of sight measurement and the conversion of that line of sight measurement to a vertical displacement.
Wonderful. So this is lots of questions coming in. We love it. So please keep the questions coming. And if we are unable to get to your questions, we will post the answers to your questions on our website with the recording. So just going to go find, there's another one here. So this one came in. So first of all, thanks for the presentation, and you're most welcome. Did I understand correctly that Catalyst Insights actually does the InSAR processing, and the user/client can just look at the scatterers and the risk, etc.? So perhaps you can explain a little bit more about what's happening under the hood and how we're providing it. And there's another question that I was asking about the quality assurance of the measurements we're delivering. So maybe it makes sense to just address that there in your answer here.
Yeah, absolutely. So that's a great question, and we do process the data and make it available via the web application that we showed. This was a sample data set that we showcased today. However, our clients who subscribe to Catalyst Insights have the clients who subscribe to our offering basically have the ability to pull up the web application and consult the information just as was described in the question. So they can look at the scatterers, they can look at the points, they can look at the trends, they can understand the risk, they can help define the risk, which is a key thing, which maybe didn't come across in the demonstration or in the presentation. You know, we're using arbitrary values to showcase the possibility of where a client can define what the risk categories are, what the displacement values would be that can help identify risk. And there's just furthermore, there's a couple of other questions around, you know, is this capability available within our software? So we do make this capability available through our Catalyst Professional software, which is our complete offering, which is more targeted to expert end users. This particular offering, which we showcased today, is meant to simplify the access to the ground displacement data for engineering applications. But having said that, the full software is available to process data as well.
So to clarify with that, I think what you're saying is that the insights that you showed today, the application there, that's a separate offering that we have where you can sign up for a subscription and we deliver the measurements to you. It's kind of like a data service or data as a service versus we actually have the algorithms available to you in our Catalyst Professional if you wish to build your own workflow using Catalyst Professional, our solution that's designed for remote sensing professionals in the field, correct?
Exactly, and there's accompanying scripts that are available for those who are comfortable working with more advanced software and Python scripts to process data themselves. Yeah.
Wonderful. So there was another one about, sorry. So can I process data in cloud environment under Catalyst? So Kevin, I think this is another great one for you to take on.
Yeah, sure. So we do make the software available on a number of cloud platforms. You have the option to, again, subscribe to our software on some of the platforms. We're on Cloud EO, which is out of Europe, GeoCloud. We also have our software workflow running on a platform known as Up42, which allows you to consume the algorithm and implement a workflow where you're essentially paying only for the use of the software for when you're using it. So there is a flexibility there to either subscribe and access the software through a more traditional means, like a virtual desktop environment on a machine on the cloud, or you could actually build a workflow either through Python on that virtual machine or through a more integrated platform like Up42, connected to data and produce this type of information automatically. We featured that in previous webinars, and I would refer the person that's asking this question to some of the other material where we've shown how that works.
Wonderful. So there's another question here where they're asking about the choice of processing techniques, and they list out a number of ones like PSI, InSAR. So perhaps you can just comment a little bit on, you know, the different options for processing that's available within the Catalyst suite for InSAR processing.
Yeah, and we have a dedicated team, just to go back to your answer on to your question about quality assurance, and maybe this helps in terms of explaining a little more how we decide how to process the data and what techniques to apply. We have a dedicated team that focuses on InSAR in our company. We've adapted the software in a way that follows the peer-reviewed literature. So our team is very advanced in terms of how they are building our software to make sure that the techniques that are well accepted within the InSAR community, which is very advanced and has a number of people contributing to it. And so we have the ability to process data for InSAR, which is more repeat pass, full image processing. So it tends to work best in areas that have ideal conditions that are not as affected by atmospheric conditions like rain and vegetation. And we've also adapted the PS InSAR techniques that are in the literature with their own processing to work in those more challenging environments, like urban areas that we showed today, or more densely vegetated areas or areas that suffer from atmospheric effects like rain and moisture and so on that can interfere with the radar signal.
Wonderful. Okay, so I think we're just going to take two more questions and give people a little bit of time back in their day. So the next one is in terms of accessing what we were showcasing today and accessing the measurement or the data feed with Catalyst Insights. So so what are the different models or pricing models that we offer? So is it a subscription or can they buy it outright? And then does this include access to the API as well as the web app that you showed today?
Yeah, so Catalyst Insights is essentially a subscription. So there's a size of an area that is typically subscribed to. So customers identify what feature it is that they're interested to monitor. They communicate to us what their area of interest is. And then we process the data, both the historical information, as you alluded to in your portion of the presentation, Sean, the historical look back based on the Sentinel-1 data so they can understand the trends, and then the continuous monitoring. So there's a look back portion and a continuous monitoring portion. And essentially what they're doing is they're subscribing to an area of interest and access to their data through the web application if they choose to use it. If they want to use their own mapping application, ArcGIS is very commonly used out there. The API is a great way to connect to the data programmatically. We distribute the data through an API that we've implemented on Amazon Data Exchange, so customers can directly consume the persistent scatter or displacement information from the API that we make available for customers. So essentially, they identify an area of interest, we perform the processing, both the historical and the continued monitoring, and then we make it available through the web application and via the API. And it's up to the customer to choose if they want to use all of it or just part of it. So far, customers have been choosing to both use the web application and consume the points via an API to give them the maximum flexibility.
Wonderful. And I think for this last question, just for those who are interested, but just want to understand a little bit more and be able to test out the measurements for themselves, are there options that we offer for to do pilot projects where potential customers can test the validity of the measurements?
Yeah, so it's actually pretty easy to set that kind of thing up. Typically, the journey would be to get in touch with us to identify the area of interest. We want to make sure that the techniques that are being used are going to produce the measurements that are of value for the particular customer. So we do encourage for people to reach out to us to identify their area of interest so we can understand the application. That's very, very important. There are sample data sets available that we can provide as well. And ultimately, if the customer wants to implement a trial, the cost to start a subscription is quite easy. It's not a large spend. So I would encourage customers to kind of go in that direction to identify an area of interest, talk to us about their application, and then we can actually turn on the service and make it available within a very short period of time. And that's really going to be the true test of whether it meets with their expectations and their business needs.
Wonderful. All right, well, with that, I think we're going to conclude this webinar. So on behalf of Kevin and myself and the entire Catalyst team, we really appreciate you spending this hour with us. And thank you once again for all of the great questions. If we didn't get a chance to directly answer your question, we will answer these questions after the webinar and post them on our website with a recording, which we will then send and notify everyone through an email. So once again, thank you for your time, and we really appreciate you being here with us. Have a great rest of your day.
Thanks a lot. Bye-bye.